This video is going to look at the second law of thermodynamics, the Carnot cycle, and entropy. The second law of thermodynamics states that heat flows naturally from regions of higher temperatures to regions of lower, which is something you kind of know. If something is hot, the heat is going to travel through until it's spread out. Someplace where you see the opposite happening would be your refrigerator. Your refrigerator takes heat out of the cold and brings it into a warmer atmosphere, which is why your fridge takes up so much electricity. Now, a heat engine is a device that uses heat to do work. A heat engine has a hot reservoir and a cold reservoir, and it uses the expansion and contraction of gas to do work. An example of this would be pistons in a car. When the pistons in the car, when the gas gets hot, it expands, causing the pistons to go up, and then it cools and comes back down. In the full cycle of a heat engine, three things happen. Heat is added at a relatively high temperature. Some energy from the input is used to do work, so that heat energy is used to do work. And the rest of the heat is removed in the cold reservoir, so it's kind of taken out of the system. Now, heat engines have a certain efficiency, which basically means you put in a certain amount of energy, you get a certain amount of energy out. And that equals your work divided by the heat energy of the hotter part. The usable work is W, and over the energy added. So how much energy are you able to use versus how much did you put in? Now, work is just your change in energy, right? So your change in energy is the hot minus the cold energy. So if we plug that in, we end up getting an equation that looks like this. So this upper one is in your reference table. This lower one is not. However, you should be able to get from one to the other with the understanding that work is just your change in energy. In this case, heat energy. Now, Sadi Carnot came up with his Carnot engine. The Carnot cycle is basically saying that an engine, to be at its maximum efficiency, can't lose any energy. So if I want the maximum efficiency from a heat engine, I can't lose any energy from friction or anything else. Duh. Okay, way to be smart, Sadie. If an engine doesn't lose any energy, then it's a reversible process. In other words, if I don't lose energy, then I can keep going and going and going. Think about a roller coaster. Or a simple harmonic motion with the spring oscillating. If it doesn't lose energy, it's going to oscillate forever. Okay, so the Carnot engine, he designed a Carnot engine, theoretically, that is reversible, which means it doesn't lose any energy, and therefore it's reversible. Carnot also came up with an equation to measure a heat engine's ideal maximum efficiency. So what's the maximum efficiency of an engine? Woot woot, go Carnot. Alright, so Sadie said that your maximum efficiency equals the temperature of the highest, of the hot part, minus the temperature of the cold part, divided by the temperature of the hot part. Note that the efficiency is only equal to 1, or 100% efficient, only if your temperature cold is 0 degrees Kelvin, which according to the third law of thermodynamics is impossible to achieve and maintain in a finite number of steps. Though they have gotten pretty close to it. Let's look at an example. 3 engines operate between reservoirs separated in temperature by 300 Kelvin. The reservoir temperatures are as follows. So we have our hot and our cold temperature. Let's rank them in order of their possible efficiency. Well, efficiency equals hot minus cold divided by hot. So E equals TH minus TC divided by TH. So let's try it for each of them. E equals 1,000 minus 700 divided by 1,000. So that's 300 divided by 1,000. which is 0.3. So it's 30% efficient. So you can use 30% of the energy that you actually put into it. The second one is 800 minus 500 divided by 800, which is 0.375. So it's 37.5% efficient. And the third one would be 300 divided by 600. 600 minus 300 divided by 600, which is 0.5, or 50% efficient. So you can use 50% of the energy that you put in. So the lower your TC gets, the better for the same drop in temperature. Now let's look at entropy. Entropy is the amount of disorder in a system. So my room always shows great amount of entropy. There's a lot of disorder. Now, according to the AP people, so your AP objectives, you should be able to determine whether the entropy will increase, decrease, or remain the same during a particular situation. So you don't actually need to know the math behind it. You need to know the concept. However, the math a lot of times helps you support the concept. So I'm going to show you two ways to figure it out. One, math, the other, concept. And you can remember it however you find it easiest. Let's start with the math. Entropy equals Q over T. So heat divided by temperature. Temperature is in kelvins, so it's always positive, because 0 is absolute 0 and it's the lowest it can be. So your temperature will always be positive. So if heat is added to the system, then Q is positive, and therefore entropy is positive. If Q is negative, then your entropy will be negative. Now, Q is positive when delta U is positive. So basically, when your temperature increases, Q goes up, which means your entropy is positive. Q is also positive when your volume, Q is positive when your change in volume is positive. So when your volume increases. So basically, as your volume increases, W increases, so you end up with a positive Q. So when your final volume is greater, then you're going to increase your entropy. That's the math. Now this makes complete sense when we look at the concepts behind it. Entropy is the measure of disorder. Higher temperatures mean that things are moving faster. So if you, let's say, have a class of kindergartners, if you give them a lot of sugar, they're going to run around, and that's going to be a heck of a lot more chaos. Also, more space means that there's more flying around and more disorder. So if you take those same kindergartners and you say, you must stay on this rug, that's going to be a lot less disorder than saying, ooh, look, here's an empty gym, go have fun. So, more space, more disorder. Higher temperatures, more disorder. Alright, that's the end of the lesson. Good luck on your homework.